basically I'm on the bottom of page 23.5 in your notes, getting into page, kind of going to be on page 890, 891 in the book. But before that, I was stepping through one example where we had a hyperbolic cylinder. So this is still on page 888, 889. But anyway, what we have is if we have, for example, 25x squared plus, minus 4y squared equals 100. I'm just going to step through this. I could divide both sides by 100, which if I divide the left side by 100, I can divide each term by 100. And anyway, so what I end up with is x squared over 4 minus y squared over 25 equals 1. And this is a hyperbola. And so we can rewrite 4 as 2 squared and 25 as 5 squared. And if I have, for a hyperbola, which is in appendix page 858, x squared over 2 squared minus y squared over 5 squared equals 1, then what we have, this is the a. So if I have x squared over a squared minus y squared over b squared equals 1, then what happens is we have an intercept at x-intercept at minus a0 and a0 are the intercepts there. So what this looks like, if I were to graph this, is over 2 up 0. Here's the x, here's the y, and then left 2 up 0 is where it crosses the x-axis here, and we got hyperbola shape here. And then there are foci. I talked about this. This is in the appendix as well. I'm not going to worry about it, but those occur at minus c0 and c0, where a squared plus b squared equals c squared. Well, a squared is 4, b squared is 25, and that equals c squared. So c squared equals 29. So c equals plus or minus the square root of 29. So basically, I've got minus the square root of 29 and the square root of 29. Of course, square root of 29 is a little bit bigger than 5 for the foci. So if I was doing the foci here, whoops, let me get back to my drawing colors. So there's 2. So over here, a little bit bigger than 5. This would be the square root of 29 here. And I don't know, they're basically, wherever you go, that's the same distance away. I think that's kind of how foci kind of work here. Same distance away, top and bottom, to that foci. But anyway, this is the graph here. But what do you notice? We don't have a z. Okay, so it's kind of it's on the x-axis. So really, what I'm trying to, if I want to draw this in 3 dimensions, then basically I can flip this, kind of rotate that x-axis out to the front and the y-axis down to the right, and then z can be anything it wants. And so what happens is, if I try and do this in 3 dimensions, I'm going to clear this off. Go back to let's just do kind of my base graph. There's y, here's z, here's x, and then I'm gonna take this x back as well, back here. But really, what I have in the plane is coming out too. I've got this for the front side of my hyperbola, and then I've got going back 2 units. That's the back side of my hyperbola, and then z can be anything it wants. So if I kind of change this, this can go up or down along the kind of the same shape path vertically. Okay, so it's kind of, this sheet is out in front towards us, and then I'm going to do a different color back behind for this. So kind of go up from that is here, and then I can go down from that in the back, same shape design. So this is in the back sheet, kind of facing away from us toward the back part of the negative minus x-axis there too. So we got a couple sheets, kind of hard to see, so I did draw it a little differently on the top of page 24. But that's kind of where we were on these cylinders. So this is a hyperbolic cylinder where Z is unrestricted. So that's kind of how I think of those. So now let's go into some other base shapes on page 890 and going forward. And these are different neat things that we have here. Let me get on here. If I have a couple things, whoops, still in red, paraboloid of revolution. Okay, so if we have a paraboloid of revolution, what would something like that look like? We also have, instead of paraboloid, we could have a ellipsoid of revolution or a hyperboloid of revolution as well. And anyway, so long story short, what we want to do is we want to utilize a cross section. And so I'm just going to give an example of this paraboloid of revolution. I'm going to use the one that's in the book, but they have y squared plus z squared equals 4x. So here in this case, we have all three variables, okay, which is a little bit different. So it's not just a cylinder that we're creating on this stuff. So how do we deal with something like this? Well, what we can do is look at one of the cross sections on this, and if we let, for example, if we let z equals 0, I'm going to try and use different colors here, so I got to get into how I change the colors. If we let z equals 0, that's a cross section. So we're going to look at different cross sections. So if z equals 0, what do we have? We have y squared equals 4x, or basically x equals y squared over 4. Okay, 1/4 y squared. So the reality is that's a parabola, right? And so when z equals 0, I'm just on the xy plane. And so if I draw it in 2 dimensions and put x to the right, like I normally do, then really what we have, instead of y equals x squared, we have x equals y squared. So instead of a parabola going up, it's actually a parabola going toward the positive. Whether y is positive or negative, x would end up being positive. So there is just like x equals y squared is a parabola going that way, but then it's 1/4 of that, so it actually becomes a little bit wider, right? It's a widening effect, so that's kind of from our base graphs. And then what am I doing with that now? I'm gonna rotate these. I'm gonna put my y down here and my x coming out front, so let me clear that off and kind of show what that looks like. So if I have, I gotta switch my colors every time. So trying to make this visually appealing for you. So here's y, here's z, here's x, and so the reality is, and of course y keeps coming that way, z keeps going down, x keeps coming back. So I'm going to try and switch the colors. But then what happened is we've got this in the we actually have a parabola, right? So this is in the xy plane. So that's in the xy plane where z equals 0. Okay. So this is a cross section. And then instead of saying now z can be anything it wants, that's not true, because z is restricted by our function. Remember, our function was given by x squared, excuse me, no it wasn't, y squared plus z squared equals 4x. Okay, so we do have different things here. So this happens to be when z equals 0. Well, now let's do a different cross section, and let's let y equals 0. So if we let y equals 0, what do we have? We're going to basically, that would go away, and we would have x equals z squared over 4, or 1/4 z squared, right? So same deal, this is also a parabola, right? This is also a parabola, and the difference is, if z is positive, x is positive, And if z is negative, x is also positive. So now I'm going to be going on the xz plane because y is 0. So I'm going to kind of show the xz plane like this. I can't get back there. But anyway, that's what it is. And then what I have is a parabola. So between the x and the z axis, it comes up and goes down just like the blue one did, but that's a vertical slice kind of through my screen. And then what I can do now is, so that's a cross section for when y equals 0. But then now what I can do, and I'm going to use, I'll just blue and red make purple. I'm going to connect this. So here's the one on top. Here's the one on the left side. Here's the one on the bottom. Here's the one on the right side. And then I'm going to go back to the top. But if you notice, that kind of makes the picture that is on page 890, where my blue and red curves there are given by green in their picture. So they have a much better looking picture. But this is kind of like a blowhorn. You know, it's a smaller, these are actually circles coming out. If you take a cross section where x equals, you know, if I said, hey, you know, x equals 3. Well, if we go 1, 2, 3 and do a cross section here, it actually looks like x squared plus y squared equals 3. So that's a circle with radius square root of 3 on that cross section. But anyway, it kind of makes like a cup shape, so to speak, sitting on the origin, of course. So if x 0, 0, 0 is on my graph, but there are no negative x values on my graph, but it's a three-dimensional look here. So that is a paraboloid of revolution. Very similarly, if I had like a minus sign somewhere in there, then all of a sudden we could end up having like a hyperboloid of revolution or something of that nature. Bottom of page 890, if you're looking at your book, hopefully. Figure 14, we have a cone, x squared plus z squared minus 4y squared, where y is greater than or equal to 0, gives a cone. If you don't restrict y and you let y be negative, we'd have 2 cones. We'd have one going out to the left as well. Okay. And so we've got some different things like that. All right, so anyway, let me move on. So there's all kinds of different graphs we can have, all kinds of fun stuff. And, you know, we're going to try and get good at a lot of it, but then also be able to recognize what these things are based on their look of the graph. Okay, so one thing we get to on page 891 is an ellipsoid. So what is an ellipsoid? Ellipsoid is kind of a football shape, and it's going to look like have this for the graph: x squared over a squared plus y squared over b squared. That's not a minus sign. Plus y squared over b squared plus z squared over c squared equals 1. Okay, if I have something like that, notice it's a plus plus the whole way. Once again, if I want, I could say, hey, let x be 0, and if x equals 0, what's the cross section of what's left? Well, I end up having an ellipse because I get y squared over b squared plus z squared over c squared equals 1, multiply through by least common denominator. Anyway, but this ends up being an ellipse. And similarly, I could do that if I let, well, let me just write that down. That's an ellipse. And if I do it with a different color, if I let y equals 0, so if this one is 0, I get x squared over a squared plus z squared over c squared equals 1. That's also an ellipse. It's kind of like a, you know, elongated circle, right? And I could do the same thing with z, right? So if z equals 0, I also get, for the same reason, I get an ellipse. So what it looks like is on figure 15, but it's a football shape, is ultimately what I get. So if this is my x. If x is 0, then I'm getting an ellipse here, basically along the slice of the board. If y is 0, actually, I should have done, we said x was 0, so I should have done that one in red. I'm sorry. If x is 0, that's an ellipse along the slice of the board. If y is 0, then I'm coming out toward you underneath the bottom, and then here. So kind of through the screen, and then if z equals 0, I get on the surface here, table surface. Anyway, long story short, that's a really ugly looking football. But I guess what I should have done is I'm getting a circle there, or not a circle, but an ellipse, and ellipse. It ends up making a football shape. So this is why I don't like drawing in general, but you guys can get more creative on your artwork. I'm just going to erase this real quick so no one knows that I actually did that. Because that was brutal. Anyway, but once again, coming up with the cross sections to see what it looks like, but also knowing what it should look like is a big deal, for you, especially like for your test Monday. A couple others. So we have elliptic hyperboloids. So we have a couple different elliptic hyperboloid. So the name does the talking here. Now there's a couple different ones. We could have one sheet, or we could have 2 sheets. Now initially I'm not going to give 2 sheets. I'm going to wait on that one. So we'll focus on giving a sheet. I mean 1 sheet. So with that being said, what does that mean? So I am on page 892. So there's nice pictures there. The 1 sheet means it's connected. Okay. And then so kind of like a cylinder was a surface or a sheet. I said we could kind of call it a sheet. Well, if you wrap that around, it's all connected. That's 1 sheet. So it's just one thing. It doesn't tear or rip. But on elliptic hyperboloid, of 2 sheets, it actually splits apart and there's no middle part to it. So let's look at the difference. So if we go 1 sheet here, this is going to have a general form of an equation of x squared over a squared plus y squared over b squared minus z squared over c squared equals 1. So notice, very similar to the equations that we had before, but I've got a minus. I've got a minus in there. Okay, so let's pay attention to that. And the reality is, if I let z equal 0, then what do we have? This would go away, and I'd be left with what? I'd be left with an ellipse. X squared over a squared plus y squared over b squared equals 1 is an ellipse. And the top on figure 16, top of page 892, is a picture of that ellipse. Now that ellipse happens to look like a circle. Remember, a circle is a type of ellipse where a squared and b squared are actually the same number, right? So I mean, it could be a circle, but it could be a little bit elongated as well if a and b are not the same value. Okay, so that'd be an ellipse. So once again, the name of the figure here, there's an ellipse in there because it's elliptic. And then what's the other thing that's in the name? Hyperboloid. So you might think hyperbola. So what happens if let's let y equal 0? If y equals 0, what do we get? We get x squared over a squared minus z squared over c squared equals 1. That's a c there. Anyway, what's that? That's a hyperbola. And that's when y is 0. So when y is 0, I'm on the zx plane, and then I'm going to get a hyperbola that's, remember, a is kind of the dictator here. I'm out a, so kind of that's a vertical hyperbola, and then going back here, if I've got 2, if a was 2, I'd be back here. So kind of like what I had in that first graph that I did today, hyperbolic cylinder, just this part, this slice where y equals 0 gives a hyperbola. And then, you know, if y could be anything at once, then that becomes a hyperbolic cylinder. But y cannot be anything at once because it's part of my equation here. So the other one that I can do is, let me change colors here to, if I let x equals 0, same deal, then I end up with this. This is also a hyperbola, and where b, so now I'm coming out b units. Well, let's say that it doesn't matter, you know, if b was 2, but anyway, I'm coming out b units wherever that is, and then that's up and down, and then I'm coming back here up and down there as well. And then what I'm going to end up doing is I'm going to connect all these with the ellipse in between. So any horizontal cross section, including when z equals 0, is an ellipse there. But guess what? I have an ellipse up here connecting. Whoa, what happened to my green one? I've got an ellipse up here connecting those, and I've got an ellipse down here, and maybe you could do dashes when you can't really see it down there. And you end up with a beautiful figure 16 that looks just like mine, except mine's prettier colors. But if you did a horizontal cross section parallel to the XY plane at z equals 5, what do you get? I'm getting an ellipse up there that's bigger than the one that's sitting on the table surface, right? So it goes out and up both sides and gets bigger as we go farther up the z-axis and farther down the z-axis. So I'm going to go ahead and erase that so we don't have any traumatic memories or bad dreams over the weekend, and we'll go from there. So, but now that was given one sheet. What about 2 sheets? Let's see if we can do the 2-sheet deal. So what's the difference in the formula? And I'm going to show you the book formula for this. Shows like minus x squared over a squared minus y squared over b squared plus z squared over c squared. This is what they show equals 1. Well, notice that what they did is, you know, this is opposite, this is opposite, this is opposite, and this is the same, right? So they had opposite on the left side. Well, I don't like that at all. So here's what I'm going to do. I'm going to rewrite this so my eyes like it better as x squared over a squared. In other words, I'm going to multiply both sides by 1. And if I do that, I've got x squared over a squared plus y squared over b squared minus z squared over c squared. Is that the exact same as what I had when I gave had one sheet for an output? It is, but what's it equal on the right? -1. Isn't that great? So I'm going to change this side to the opposite sign, and so when it is a -1, that does not give me when z equals 0 here. Then I'm going to use a color I haven't used, so orange. If z equals 0, and I eliminate that one, then I've got what normally would be an ellipse if it equaled 1, but it doesn't equal 1, so I don't get an ellipse. So what do you get? What numbers, when you square them and add them together, give you a negative number? In other words, let's look at what's left for the z equals 0. X squared over a squared, we know that's positive, correct?
There is a
Y squared over b squared, we know that's positive. If you take, or non-negative, it can't be negative. That's what we know. It could be 0 if x is 0, y is 0. But anyway, this is greater than or equal to 0. So when could it equal -1? Never. So there is no graph for, you know, if x and y are positive, there's no graph allowed here. So in other words, you don't get the ellipse. There is no ellipse on an elliptic hyperbola. Not for a while. Well, not until no ellipse for a while. Now, what do I mean for a while? Well, when z equals 0, if x and y are not 0, you're not going to get one. But if I go up to 10, you know, if z equals 10, could I get an ellipse? Well, I could, because now this is another number, and I add, let's just say c equals 1 and z equals 10. Now I'm adding 100 to both sides, and the right side becomes 99. Then I could get an ellipse. So if you look at figure 17, which I'm gonna try and draw this, but if I'm looking at figure 17 and I've got kind of this deal, that looks pretty good. It's like an upside down ball cap, kind of, with no lid on it. But if I take a cross section of this, I'm going to take a cross section. I'm going to say where z equals 10, right there. I would have an ellipse there, right? So if you go up high enough or down low enough, you get a cross section for an ellipse. Now, which one had the ellipse was the Z one, right? So the Z one had the ellipse, correct? And if I go down 10, then my cross section would also be an ellipse, my parallel to the table plane would be an ellipse. But what do we notice? So here, let's go back to the formula that we had. We had x squared, my version of it, x squared over a squared plus y squared over b squared minus z squared over c squared equals -1, right? But which one had the minus over here? The z did. So which way do your sheets face, two sheets face? The z-axis. They follow the z-axis because that's the one that had the minus sign. So that's the other advantage to keeping it my way, is that you know that follows up and down. I'm going to do one more real quick, try and graph it. You can go. I'm going to go for another 15, 20 minutes, but basically finish the homework for 10-6. I'm going to try and do one look at a hyperbolic paraboloid as well, and maybe an elliptic cone, along with one more example of this, and go from there. So hopefully that's enough. Watch, yep, you bet. Watch the rest. I'll see you tomorrow. You can ask me questions at halftime of your game or after your game.
I'll probably be thinking about calc.
Yeah, probably be thinking about calc. Probably not. But anyway, I will be around Saturday and stuff. But anyway, available by WhatsApp. If I'm not answering, text me individually because of my storage issues.
Interruption. Lauren Bell and John Antover, could you please come to the front office?
John.
Lauren Bell and John Antover.
Okay.
Please report to the front office. Thank you.
Ready?
See you later. You bet. Test Monday.
Gotcha.
Okay. So let me just do a specific example of a elliptic hyperboloid of two sheets. So let's look at, if I've got x squared over 25 minus y squared over 9 plus z squared over 16, and I'm going to say that equals -1. So I've already set this up to look like my formula here. So this actually has two sheets, and what I may do is I may come back and rewrite that and say it equals +1. But anyway, where is the minus sign attached to? It's attached to the one with the y value. And so the reality is those two ball caps are going to be going along the y-axis. Okay, so if I'm going to graph this thing, it's going to go along the y-axis. And here's z, here's x. But anyway, so if I let y equals 0, I'm going to go back to red. If we let y equals 0, then essentially I would have a circle if this ends up being equal to a positive number, but it doesn't, so I don't have anything there, right? So y has to be big enough. So when does y get big enough? Well, if y equals 3, so y equals 0, there's no graph, right? But at y equals 3, y equals 3, what do I get? I get 3 squared over 9 is 1. I got minus 1, I add 1, and then I get x squared over 25 minus plus z squared over 16 equals 0. Well, that's only true when x is 0 and y is 0. So over at 3, I get 0. Now also when I go left 3, I could plug in y equals negative 3, I get 0. But then if y equals something bigger than that, like if I have y equals 5, then what I'm going to have is y squared is 25 over 9, which is not quite 3, but I'm going to add not quite 3 to negative 1, and then I end up with a circle. So what happens on a cross section there, when y is a specific number, I'm going to get a circle out here that gets bigger and bigger and bigger. So the reality is what happens is I end up with, you know, a bigger and bigger circle. So this is how it goes. I should have dashed that back there. So once again, this is a better way. If you dash what you can't see, I could kind of see all the way on the end there, but it does keep going out and wider forever. But it's going along the y-axis. So the reality is we get a three-dimensional kind of cone shape. This is an elliptic hyperbola of 2 sheets. Why? Because it equals -1. It fits this format, and it goes along the y-axis because that's where the minus sign is. Okay, now I'm going to just change this a little bit and say, okay, well, hey, what if that actually equaled a positive 1? How does that change the graph? So let's just look at that quick. So I'm going to see if I can just erase versus part of it versus all of it. Whoops. Eraser. Hey, look at that. Isn't that cool? Okay, so if I have this, okay, now let's just erase part of that. All right, get back to drawing. Let me fill in my axes here. I got to admit, this is working out better than I thought today's session would go. It does help when I don't shut off the student being able to do this, to draw on this and stuff. So anyway, if I'm doing this and say, okay, now this equals +1, let me get, I need to erase a little bit more. Let me erase this stuff. At least erase it good enough. Okay. So if I'm doing that, then, and I've got this equal to 1 here, get back where I can draw. So this equals 1. Now what we have is we have an elliptic hyperboloid of 1 sheet. But if you notice figure 16, where was the minus sign for that one? And it was on the Z, and so basically your 1 sheet would follow along the Z axis. Well, where's my minus sign here? It's still on the Y. Okay, so the reality is my hyperbolic sheet, 1 sheet, is going to follow along the y-axis. But now if I let, whoops, but that minus sign is with the y. So if I let y equals 0, what do I get now? Well, now I get x squared over 25 minus, or not minus, plus, minus 0, and then plus z squared over 16 equals 1. That is an ellipse, right? Where x goes out to 5, and then it would go back to -5, and then z goes out to 4. No, z, not let's see. So if x is 0, then we get a z. So it's up 4. Sorry, I need to erase that. Eraser. I didn't mean to put that one there. So if z is 0, x is 5, right? Because 5 squared over 25, or minus 5. And then if x is 0, z is 4, or minus 4. So I go down here, minus 4. Okay. Let me change that here to minus 4. But anyway, so what I end up having then is an ellipse, right? An ellipse that, if I assume I can't see it, make that dash, but that's an ellipse kind of through your screen. So on the XZ plane through the screen, I get an ellipse. So it's actually a little farther out towards us and farther back away from us than it is up and down. So it is an ellipse because of these numbers here. So we get that. And then what happens when y is, let's say y equals 3, well, then this ends up being 3 squared is 9 over 9 is 1. I add 1 to both sides, and I end up getting a bigger circle out here. So, or not circle, bigger ellipse out here, bigger ellipse out here. And of course, I didn't follow my rule of saying dash it. And so what happens is I get out even farther, it's going to get even bigger and bigger. And bigger is better, and better is bigger, right? Anyway, and then I just connect all that. I kind of ran out of room on the bottom. I don't know if you can see that or not. I can't really see it on mine. But anyway, the top side looks pretty good. But long story short is that one sheet that we had at the top of figure 16 on page 892, instead of going along the x-axis, where am I going along? I'm going along the y-axis because that's where the minus sign is. So trying to give you easy ways to know that. And it equals +1, which means it's one sheet. If we have, a format like this with one minus sign in there, but once again, x squared, y squared, z squared, then equals -1, then it's going to be 2 sheets. So hopefully that's a good way to know that. And then essentially, we have central quadrics graphs. So central quadrics have graphs of the form plus or minus x squared over a squared, plus or minus y squared over b squared, plus or minus z squared over c squared equals 1. This is why they tried to make theirs match equaling 1. I prefer it the other way because I want to know if it's one sheet or 2 sheets when there's exactly one minus sign in there. So remember, if there's no minus signs and these are all positive, we're going to get a football shape. Okay. But if we have one of these being negative and it equals 1, so I'm just going to pick one. I'm going to say, let's say that this one is negative. Then I'm going to have an elliptic hyperboloid of 1 sheet, since it equals +1, and that 1 sheet is going to come out of the board toward us and away from us along the x-axis. It's going to wrap around that, so to speak. And then, of course, if I have this equaling -1 and I've got a minus sign on the x and the other 2 are positive, this is an elliptic hyperboloid of 2 sheets, so also going out towards us from the x-axis and away from us along the x-axis, but it's like 2 ball caps without the lid that extends off the cap part. So anyway, hopefully that makes sense to you on those. And then we'll just have a couple of more quick examples. Well, I don't know how quick they're going to be, but I'm going to stop the video now and try and